Hello everyone. Last lecture we talked about the electric potential. I want to discuss about the electric potential due to dipole, electric dipole today. Okay. Electric potential electric potential due to electric dipole. Let us suppose you have two charges, negative Q, and here you have positive Q. They are equal but opposite, and the distance between them is L. Two equal and opposite charges separated by a certain distance, that is called as the electric dipole. And I would like to calculate the electric potential at this point, let it be point P, due to this electric dipole. Let us suppose the point P from charge negative Q is R, and the point P is at a distance 1 second. The point P from positive charge Q, let me call R. This is little bit longer, so I have to draw from here, from this point to point P is R. So let it be, this is delta R. So the distance of point P from the negative charge is delta R plus R. Now we need to calculate the electric potential at this point P due to this electric dipole. But I gave you the formula to calculate the electric potential due to point charge, which is V. The electric potential is K Q divided by R. This is the formula to calculate the electric potential. And I told you that electric potential is a scalar quantity, so we don't have to use any vector law. We can use very simple algebra here. So electric potential at point P, electric potential at point P is, let me write down V, that is electric potential due to this negative charge and electric potential due to this positive charge. So let me write down electric potential due to this positive charge is K Q divided by R, because the distance from here to there is R, plus electric potential due to this negative charge is K negative Q, divide this by R plus delta R. That's it. So we add the potential due to this charge, positive charge and negative charge. Now let us simplify this. If you simplify this, you get R plus delta R. Then here it is KQ times R plus delta R. You have minus here, so you can write down negative KQ times, here you have R plus delta R, so you have just R only. Okay, so if you simplify this, V, this is equal to, look, here you have a KQ, here also you have a KQ, so you can pull out this KQ. Here you have R plus delta R, R plus delta R, minus you have R there, and divide this by R times R plus delta R. Okay. So what happened then? You can write down V, this is equal to, this R and negative R cancel out. So KQ delta R divide this by R times R plus delta R. Here L is very large as compared to delta R, as compared to R also. Delta R is very small as compared to L, as compared to R. So we simply neglect the delta R, then it becomes, if you neglect the delta R in the denominator, it is 0, very small, approximately. So we neglect in the denominator only. If you neglect here, then everything becomes 0. We don't do that. So we neglect this delta R. Okay. So if you do that, then you get K Q delta R. Divide this. If you neglect this tends to 0. Then you will have only R square then. Now look at this delta R. What is this delta R? If you consider this angle is theta, what is delta R then? Let me write down delta R divided by L. This angle is 90 degrees. So if you use this angle, what is delta R over delta R over L? So delta R is adjacent, L is your opposite. So adjacent over opposite is cosine, and your angle is theta. So delta R, this is equal to L cosine theta. Okay. Okay, so V, this is equal to K Q, delta R is L cosine theta divided by R square. So this is the potential due to electric dipole. But this Q times L, this term Q times L, okay, this is called as dipole moment. This is called as dipole moment, which is Q is in coulomb, length is in meter, coulomb per meter. Okay, coulomb per meter. So this formula, if you want, you can write down. Your electric potential due to electric dipole, this is equal to K P, this is dipole moment, cosine theta divided by R square, where P is QL, coulomb meter, and this is dipole moment, and the unit of dipole moment is coulomb meter. But people, they also use very small unit, that is called as dBi also. But you can use this coulomb per meter. So this is the electric potential due to the electric dipole. What is the electric potential due to point charge? This KQ divided by R. So simply the electric potential, if you move away from the charge, source charge, your potential decreases according to R. But in case of electric dipole, it also decreases, but according to R square, with R square here. Okay, so that's the difference. So this is the potential due to electric dipole. Okay, and we already discussed about the electric field, and we just did the electric potential. And if you have a, let's say this is your conductor, this is your conductor, this is charge. The charge is always on the surface of the conductor, like this. There is no charge inside the conductor. I already mentioned that. And there is no electric field inside the conductor. Electric field is 0, but electric potential inside the conductor V, this is constant. So better to know this. Electric potential inside the conductor is constant. Good to know this. Okay. So this is all about the electric potential things. Next, I want to talk about capacitor. This is the device to store the charge, or you can say energy. Okay, the device used to store the charge, that is called as the capacitor, and capacity to store the charge is called capacitance. Capacitance, you can write down C. So, device to store the charge, that is called as the capacitor, and the capacity, ability to store the charge, that is called as the capacitance. It is simply represented by uppercase C. Okay, and the capacitor has a two plate like this. This is one plate, and you have another plate, this. Something, you see, I have parallel plate capacitor. Okay, this is the capacitor, and it is parallel plate capacitor. It has a two plates. Look, one plate, another plate, and this is parallel plate capacitor. And you can move, you can change the distance between two plates as needed, because the capacitance of the parallel plate capacitors depends on area of the plate. This area depends on the area of the plate, and the capacitance also depends on the distance between the plate. So if you want to check that, you can change the distance between the plate. Of course, I cannot change the area. Okay, this area is kind of constant, otherwise I have to break this capacitor. Okay, so I cannot change the area, but I can change the distance between these two plates, and this is the parallel plate capacitors. If you want, you can keep something here, insulator. You can keep some kind of insulator, like a paper, plastic, whatever you want, you can keep here. We call that dielectric. Okay, but right now there is nothing, just the air here, or we can consider just like a vacuum. Okay, so this is the parallel plate capacitor, and this capacitor, we can use this to store the charge. Okay, so let us suppose we have a parallel plate capacitor, or you can use any capacitors. The charge on this is positive, on this is negative. Let's say the charge is Q. The distance between this plate is, you can consider D, and you know that if you want, the electric field is always from positive to negative charge. So this is the direction of electric field, and let us suppose the potential difference between these two plates is V. The potential difference between these two plates is V, and you know that the charge is stored in the capacitor Q. This is the charge stored in the capacitor Q. It depends on the potential difference. What you will do? In the beginning, there is no charge. You connect to the source. You give the one charge, positive charge. Then, if you want to add another charge, you have to do the work. That is how you store the charge here, and you store the energy. So that this Q is directly proportional to the potential difference. Okay, so the charge in the capacitor is directly proportional to the potential difference between the two plates. So you can write down Q, this is equal to C, this is the capacitance, times V. Q equal to C times V. Here, this C, it is proportionality constant, and it's called as, C is the capacitance. Okay, the capacitance of any capacitors, it simply depends on shape and size of the capacitor. That means the distance between the two plates and the area of the plate. That is why we can say that the capacitance of capacitors depends on shape and size of the capacitors, and it can also depend on the whatever you keep in between the plate, dielectric also. So this C, this is the capacitance, and if you want to capacitance C, from here you can write down C equal to Q divided by V. C is Q divided by V, so it is Coulomb divided by volt. Coulomb per volt, and this coulomb per volt, this is called as farad, or simply you can write down F. F is the farad. Okay, so the unit of capacitance is farad, SI unit. But you can see the smaller unit like a millifarad, microfarad, even picofarad, like that. So if you have, let's say, 1 millifarad is 1 times 10 to the power negative 3 farad. 1 microfarad, this is mu, microfarad is 1 times 10 to the power negative 6 farad. If you see the picofarad, PF, this is picofarad, this is equal to 1 times 10 to the power, I think it is 12, please check, 10 to the power negative 12, 10 to the power negative 12 farad. So you need to know this conversion. Okay, so this is the capacitance, the capacity to store the charge, the capacitance of the different capacitors. There is a spherical capacitors, there is a cylindrical capacitors. I already showed you the parallel plate capacitors. Okay, so the capacitance that depends on shape, size, and whatever medium you have in between the plate, that determine the capacitance. Okay, and these capacitors can store the energy, and the energy stored in the capacitor, that is potential energy, the electrostatic potential energy, and the electrostatic potential energy U, this is the energy stored in the capacitors. U, energy stored in the capacitors. This is 1/2, okay, Q times V. This is the energy stored in the capacitor. Energy stored in the capacitor is 1/2 Q times V. But you know that Q equal to C times V. Okay, so this is the formula to calculate the energy stored in the capacitors. But if you want to write down in different way, you can write down 1/2. What is Q? Q is C times V, and you have another V there. V is the potential difference. So your potential energy or energy stored in the capacitor, this is 1/2 C V square also. This is the energy stored in the capacitors. Okay, or again look here. What is V then? V is Q divided by C, right? From this formula. So if I use this, Q equal to 1/2 Q times V, your U equal to 1/2 Q. What is V? V is Q divided by C. V is Q divided by C. So your potential energy, this is 1/2 QV square divided by C. This is also the energy stored in the capacitor. So as needed, you can use this formula, or you can use this formula, or you can use this formula. So this is the energy stored in the capacitors. Okay, so this is important formula, so please don't ignore. I told you that there are different types of capacitors: spherical capacitors, cylindrical capacitors, parallel plate capacitors. So how do you calculate the capacitance of the parallel plate capacitors? Let us do that. Parallel plate capacitor. I showed you the parallel plate capacitors. This is your parallel plate capacitors, right? This plate and this plate is parallel, so we call parallel plate capacitors. So let us consider this is parallel plate capacitor. Consider this is parallel plate capacitors. This is positive, this is negative. The distance between them is D. Electric field is E. The potential difference between these two plates, if you can consider V. Okay, and charge in the capacitor is, you can call Q, uppercase Q or lowercase q, that is not a problem. And let us suppose these are the plates, so we can think about the surface charge density. The surface charge density, what is this? This is surface charge density. Surface charge density, sigma. And let us suppose the area of the plate is A. A is the area of the plate. Okay. And if A is the area of the plate and Q is the charge, the surface charge density sigma is equal to charge per unit area. This is called as the surface charge density. So Q, this is equal to sigma A. And in our previous lectures, we talked about the Gauss law. Okay, we talked about the Gauss law, and from Gauss law, the electric field E, due to the the charge conductor, the plate is, what is this? This is sigma divided by epsilon 0. Here the electric field is sigma divided by epsilon 0. But our goal here is we would like to calculate the capacitance of the parallel plate capacitor. So what do you think? How do you calculate the capacitance of the parallel plate capacitors? You know that there is a relationship between electric field and electric potential. E dc is equal to electric potential divided by D. This V is the potential difference. Okay, V is the potential difference and D is the distance between the plate. And from the definition of capacitors, Q equal to C times V. Okay, so what is V from here? Look, E equal to V divided by D. What is V? Isn't it E dc is equal to, not E, sorry, V. What is V? V equal to E times D then. So if you plug this V right here, what happened? Q this is equal to C. V is E times D, CED. This is your Q equal to CED, right? So what is C from here then? C is Q divided by E times D. Okay, so let me rewrite. C, this is equal to Q divided by E D. Okay, so what is E? This is C equal Q. E is, this E is sigma divided by epsilon 0. Look at this, E equal to sigma divided by epsilon 0 and D. Okay, so look at this. And what about the Q then? Q equal to sigma A then. From here, look, your C, there is a Q. Q is sigma A, so I want to write down sigma A, divide this by sigma divided by epsilon 0 times D. But this sigma and this sigma cancel out. So if you simplify this, you get capacitance C. This is equal to epsilon 0 times A divided by D. So this is the capacitance of the parallel plate capacitors. The capacitance of the parallel plate capacitor, this is equal to epsilon 0 times A divided by D. You know the epsilon 0. Epsilon 0 is the permittivity of the free space, or you can call air also. We consider air and free space kind of similar. They are not exactly, but we consider that. So the capacitance of the parallel plate capacitors is epsilon 0 A divided by D. So if there is a air in between the plate, you can use this. You can use this formula. Okay. But if you have something like, let us suppose now you keep something here, you keep some material here, like this, insulator, okay, this is insulator, and this insulator we call dielectric material, okay. If you keep the dielectric material in between the plate, then your capacitance C, this is, you can write down K epsilon 0 A divided by D. Here this K is, this is dielectric constant, okay. This is dielectric constant, not Coulomb constant, this is dielectric constant, okay. Now you can write down like this, K epsilon 0, you can just simply write down epsilon only. Not epsilon 0, just epsilon A divided by D. This is epsilon is K times epsilon 0. So what is K then? Your K dielectric constant is epsilon divided by epsilon 0. Okay. So if you have a dielectric medium in between the plate, then this gives you the capacitance of the parallel plate capacitors. Here you have a epsilon. Epsilon is permittivity of the medium, material medium, not the free space. Epsilon 0 is the permittivity of the free space, but epsilon, this is permittivity of the material medium. Okay, so this is the capacitance of the parallel plate capacitors if there is a medium in between the plate. Okay, if there is no medium, just simply the air. If there is simply air, then in that case your capacitance is, let's say, C equal to epsilon 0 divided by epsilon 0 times A divided by D. Then you can see from here the capacitance, it depends on area of the plate. This is area of the plate, and this is the separation, the distance between the plate. The distance between the plate. Okay. Now how do you calculate the energy stored in these capacitors? The energy U, what is this? The formula is 1/2 C V square, right? This is the formula, one formula to calculate the energy in the capacity stored in the capacitors. E, this is equal to V divided by D, magnitude only. I did this somewhere in previous lectures. This is the relationship between electric potential and the electric field. Okay, so what is V then? V is ED. And in this formula, what is C? What is C? What is capacitance? I'm doing the parallel plate capacitor. So capacitance of the parallel plate capacitor is this, epsilon 0 A divided by D. You don't have to write down, it's already there. Okay, so C is epsilon 0 A divided by D. V is E times D. Let us plug this number. What happened? 1/2 C is epsilon 0 A divided by D. This is C. And V is E times D square. Okay, so let us see what happened. 1/2 epsilon 0 A divided by D times, this is E square D square. Now look at this. This square, you can cross out this D. Okay, then your energy U, this is equal to 1/2 epsilon 0. I want to write down E square first. E square times, you have a here, A, and you have a D there. E square is cancel out, so you still have a D here. This D, A times D. Now look at this. If you multiply this area and this length, do you know what you get here? You get the volume. It is something like this. If the area is, let's say this is the area A, this area, if you can draw like this, if you have like something like this is the area, cross-sectional area base, and if you multiply this is your D. If you multiply, it's like a cylindrical or whatever, like you can have rectangular also. So if you multiply this area by the height length, you get the volume. Okay, so A times D is the volume of your capacitors there. So you can write down U, this is equal to 1/2 epsilon 0 E square times, I can simply write down volume V, not potential. This V is not potential, this is the volume. Okay, that's why I write down here volume. Okay, if you divide by volume V here, volume V here, and volume V there, of course this is cancel out. Energy divided by volume, we call this is energy density. Therefore the energy density, this is equal to 1/2 epsilon 0 E square. Sometimes you need this to calculate the energy density. Therefore energy density is energy per unit volume. That is what we call the energy density. And energy density is equal to 1/2 epsilon 0 square. Okay, 1/2 epsilon 0 square. Okay, so this is what you have in chapter 17. Okay, now in the same lecture I want to start chapter 18 and chapter 19 together, because they are about the electricity, current, electricity things. So I want to start from current. Current, it is simply denoted by I. Current is a scalar quantity. First you need to know what is current. The current is the rate of change of flow of charge. Okay, the rate of, simply you can say the rate of flow of charge. The rate of flow of charge. How fast the charge moves. Rate of flow of charge. That is called as the current. So you can write down current I. This is equal to delta Q. Q is the charge. If you divide by time, then this gives you the current. Rate of flow of charge. That is the current. And look at this. Your charge is coulomb and time is second. Coulomb per second. Coulomb per second, that is the unit of charge. Current. The unit of current is coulomb per second, but we don't use coulomb per second. This is the coulomb per second. This is good, but we call this is ampere. Ampere, you can write down simply amps, or even you can write down A. That's the same thing. Coulomb per second or ampere, or you can call amps, or just simply write down A. That's the same thing. That is the unit of current, SI unit. Okay, so rate of flow of charge, that is the current. Okay, and you know that the rate of flow of charge, we have two types of charge, electron and the proton. Proton is always in the nucleus, in the central portion of the atom. Proton, they do not move, simply the electron move. Actually that is the flow of electron. Okay, so this is the current, and there is another term, resistance. Resistance, we simply write down R, okay, to represent the resistance. Like if you push something on the floor, on the ground, motion, the object is in motion, but there is a force in the opposite direction of motion, we call that friction force. Friction force opposes the motion. You did that in mechanics, physics 120, right? The friction force opposes the motion. So here in current electricity, the electron is moving, but there is a the property there that opposes the flow of electron, opposes the current, opposes the flow of charge. That is called as the resistance. So resistance opposes the current. Resistance, it opposes the flow of charge. Opposes the flow of charge. That is what we call the resistance, and it is simply denoted by R, and the unit is ohm, and you can use this symbol omega. This is the omega. Okay, so if you have a conductor, there are three types of material: conductor, insulator, or you can call bad conductor, and there is another one, semiconductor. So forget about the superconductor right now. So if you want, you can include that: conductor, insulator, semiconductor, and superconductor also. But I am not planning to talk about the superconductor in this chapter. Superconductor, simply if your temperature is very, very less, while below the 0 degrees Celsius, and there is no resistance, you have a material, something like that, we call that superconductor. You can forget about that right now. So the resistance, let us suppose this is a conductor, metal conductor, like a wire. This is the wire, okay, or like a rod. And this is your area of cross section A. And this rod has a length L. If you connect this, if you apply the potential difference, then the current flow through this conductor. That means like this: if you apply the potential difference, you can connect to the battery like this. Then the current flow through the circuit. So this is a battery. This is the long line is positive terminal. The short line is negative terminal. You know that the battery you always draw like this. This is a battery. Battery you draw like this, and if you have to draw the capacitor, this is a battery. Okay, don't confuse. This is a battery. If you want to draw the capacitors you can draw this way, equal line. This, or you can also draw this way, capacitors, both. This is also, you can use either. So this is capacitor. Okay, so I have a conductor like a wire, or you can say rod, and the length of the rod is L, and the area of cross section is A. Now I want to figure out what factors determine the resistance of the conductor. Okay, what factors determine the factors that determine the resistance of the conductor. Basically, there are two things. One is the area cross section. That means the thickness of the wire. If you have a really thick wire, what happens? If you have a really thin wire, what happens? And if you have a really long wire, or you have a very short wire, what happens? So the thickness, or you can say area of cross section, and the length of the conductor, that determines the resistance of the conductor. So let me write down: the resistance R of the conductor is directly proportional to the length of the conductor. If you have a long wire, a long conductor, long rod, whatever, your resistance is more. Okay, long wire has a more resistance, short wire has a smaller resistance. Therefore, you can say that the resistance is directly proportional to length. Length increase, resistance increase. Length decrease, resistance decrease. But the resistance is inversely proportional to the area of cross section. That means if you have a thick wire, resistance is less. If you have a thin wire, resistance is more. You can compare with water pipe. If you have a really wide pipe, water move fast, you know that, right? So easy, don't say fast, easy. If you have a wide pipe, water move easily. If you have a really narrow pipe, it moves, it's difficult. Okay, so the resistance is directly proportional to the length of the conductor, length of the wire, and inversely proportional to the area of cross section. Okay, so you can write down your resistance are, this is equal to, I have a proportionality sign, I have to put some constant here, we call that proportionality constant, and the proportionality constant here is rho. This rho, this is the proportionality constant, and you have L divided by A. This is the formula to calculate the resistance of the conductor. So where rho, this is rho, okay, this is rho, proportionality constant, and this rho is called as the resistivity of the conductor. And resistivity, it depends on the material characteristics property. Resistance, if you have a long, let us suppose you have a copper wire. If you have a long copper wire, you have a bigger resistance. If you have a short copper wire, you have a smaller resistance. Or think like iron. If you have a long iron wire, more capacitance. Short iron wire is smaller capacitance. Resistance. One more time. If you have a long wire, let's say iron or whatever metal wire you have, if you have a long wire, resistance is more. If you have a short wire, resistance is small, less. But resistivity, it does not depend on length. It simply depends on the material. So the resistivity of the iron wire is constant. No matter you take a long wire or short wire, it is characteristics properties. But of course, the resistivity of the copper and iron is different. Okay, so the resistivity is the characteristics property of the material. Copper and iron wire, they have a different resistivity. But if you have two wires made of same material, one long copper wire, another one is short copper wire, both they have a same resistivity but different resistance. Okay, so rho is the resistivity of the conductor. Okay, so what is the unit of resistivity then? You can do that. Look, resistivity rho, this is equal to R times A divided by L. So R is ohm, area is meter square, length is meter. So this meter cross the square here. So it is simply ohm meter. Therefore, the unit of resistivity is ohm meter. The unit of resistivity is ohm meter, but the unit of resistance is ohm only. Okay. So we are talking about the resistance, the property that opposes the motion of the electron, the flow of the electrons, and the resistance also depend on temperature. Let me remind you, in physics 120, heat and thermodynamics, you learn that the final length of the the rod is initial length L0, 1 plus alpha delta T or delta theta, whatever you call. Linear expansion, you did this in linear expansion. That means the length of the conductor, in heat and temperature chapter, that is chapter 13, if you use the G and Coley, okay, over there we learn linear expansion. and the final length is equal to L0 initial length times 1 plus alpha delta theta. This alpha here is coefficient of linear expansion. Here in electricity chapter also, the resistance R, it also changes with temperature, and you can write down in the same way R equal to R0. This is initial resistance, or you can say at room temperature. This is equal to 1 plus alpha delta T. Or you can write down R equal to R0. This is final resistance. This is initial resistance. 1 plus alpha, change in temperature is T minus T0. Okay. T0 is the initial temperature, T is the final temperature. Okay. So here R final resistance, R0 initial resistance, T final temperature, T0 initial temperature. What is alpha? Alpha we call temperature coefficient of resistivity. So please keep in mind the resistance also changes with temperature, and you need this equation if you have to calculate. Okay, initial resistance, final resistance, or alpha initial temperature, final temperature, whatever, you can use this formula. Okay, similarly the resistivity also changes with temperature, and the formula is kind of similar. The resistivity rho, this is rho 0, 1 plus alpha T minus T0. So this is the formula. Okay, here rho final resistivity, rho 0 initial resistivity, T final temperature, T0 initial temperature, alpha is same as this, the temperature coefficient of resistivity. Okay, so please don't ignore this. Sometimes you need this formula. Okay, so this is about the resistance. Okay, so I'm not done yet. We have to talk more about the resistance and the resistor. So you have a resistor. Resistor is like a device, one component of the circuit. Resistance, that opposes the flow of current, flow of charge, and resistivity, that is the characteristics property of the material. Resistance, resistivity, resistors. We'll talk more about the resistors. But now I want to talk about the Ohm's law. One of the important law, very basic law. And the Ohm's law is relationship between I, current, V, voltage, potential difference, and the resistance R. Ohm's law relate I, V, and R. So what is this? Look at this. Let us suppose this is your resistor. Resistor having resistance R. R is the resistance. This is how you represent the resistors. Okay. If you have to draw the resistors, you draw like this. This is a resistor. Resistor. And this resistor is connected to the. This is switch. And this is connected to the battery. Is there any current in the circuit right now? Look, this circuit is off, so no current right now. It is open circuit, no current right now because the circuit is off here. Now if you join this, turn on, now the circuit is closed circuit, and the current is flowing through the circuit through this resistance R. So what is the direction of the current? This way. Is this direction of current from negative terminal to positive terminal? Think about it. Electron is here, and I told you that only the electron move, not the proton. So this makes sense. This is this, you see, look here, this is real electron flow, but we do not use this direction. We use from positive terminal to negative terminal the other way, this way, positive this way. This is conventional current, this direction, conventional current. We always use this, positive to negative. The person who discovered these things, current first, he thought at that time positive to negative. We are still using the same direction, and this direction is called as the conventional current direction. Okay, so the direction of the current is always from positive to negative. Okay, so now let us talk about the Ohm's law. What is Ohm's law? I told you that the Ohm's law gives you the relationship between the current, voltage and the resistance. So what is the statement then? The statement is the current I is directly proportional to the potential difference. Current is directly proportional to the potential difference. Again, current is directly proportional to the potential difference. So you can write that, it's really simple. You can write down I, this is equal, you can put some constant here, and this current is directly proportional to the potential difference if you keep the temperature constant, okay, temperature constant. And in this case, you can write down 1 over R, this is my constant, and you have a V. So from here, you can do this, V, this is equal to I times R. So this is your Ohm's law. Very nice formula, V equal to IR, Ohm's law, relationship between voltage, current and the resistance. That is the Ohm's law. Current is directly proportional to the voltage. Okay, if you plot the graph, between, let's see, let us suppose here you have a voltage and you have a current I there. If you plot the graph between the voltage, potential difference and the current, and if your resistor here is conductor, like a metal conductors, your graph is something like this. The conductor that obeys the Ohm's law, that is called as the ohmic conductor. Ohmic conductor. What is this? Ohmic conductor obeys the Ohm's law. Obeys Ohm's law. So, if you have an ohmic conductor, you will get this kind of graph. This is a straight line. Okay, and if you get the slope, this is your delta I and this is your delta V. So what is this? What is delta I divided by delta V in this graph? What is this? That is the slope, but what is that quantity? Delta I divided by delta V. This is 1 divided by R. Not R, 1 divided by R. Because you get, look, if you do this, you get delta V equal to delta I times R. Same as this, V equal to IR. So this graph is for ohmic conductor. Okay, this is for ohmic conductor. So what are the examples of ohmic conductor? Copper, iron, aluminum, all metal conductors, they are ohmic conductor. Okay, there is another type of conductor we call non-ohmic. If you plot the graph, if your conductor is non-ohmic and if you plot the graph, voltage here, current there, if it is non-ohmic, you get something like this. You increase the voltage, your current is slightly increasing, slightly, and after a certain point right here, it goes up abruptly. Look, here in this region, current increase slowly, but right here, we get avalanche here, breakdown. Okay, so this is non-ohmic conductor. Non-ohmic conductor, they do not obey the Ohm's law. You cannot apply the Ohm's law. That's the deal. If it is the ohmic conductor, then you will get a graph like this. It is a non-ohmic conductor. This conductor, it does not obey the Ohm's law. For example, like a semiconductor. Semiconductors are non-ohmic conductor. Okay, So Ohm's law, please don't forget V equal to IR, you need that, okay? And we have to use the Ohm's law to analyze the circuit, to calculate the current, to calculate the resistance, voltage, and so on, okay? So I want to stop here, guys. Again, the lecture is almost an hour long. I told you I cannot go more than longer. So I'll bring another video. So I want to stop here. Thank you.